Morning, everybody. My name is Tristan Banfield, and today I'll be speaking about the thermal tolerance of the important recreational and endangered white Steenbras, the Lithognathus. So the white Steenbras is an endemic species to South Africa. Its distribution ranges from the Orange River to KwaZulu-Natal. It is an estuarine-dependent species where the juveniles use the estuaries as nursery habitats, while the males use the marine habitat as their main habitat and as a spawning site. Yeah. So this species is very important, and as in the past, this species was the main catch of commercial sei netting in the 1800s to 1900s. It is also a highly prized and heavily targeted recreational fish today because of their large size and their strong fighting ability. It is also very important to our economy as it adds value to tackle shops and charters and also provides tourism. But it has many threats. As mentioned in the past, there's been commercial sei netting, and this has devastated their stocks, as in the mid-1990s it was recorded that 86 tons of white Steenbras was harvested annually. This has led to their stocks becoming collapsed. In the present day, there are increasing anthropogenic pressures, like recreational and small-scale fishermen, which do not abide by regulations, as they do not. They take over bag limit, and also they take undersized fish. This has resulted in there being a growth overfishing and also a recruitment overfishing result. In addition to these threats, there's also climate change, as trends have been seen where the sea surface temperature is increasing. There's an increasing in marine heat waves, increased upwelling events, and also estuaries are one such environment that are heavily threatened by climate change, as estuaries are a dynamic transition zone where there is fluctuating parameters such as the water temperature, oxygen, salinity, and therefore these parameters can be greatly affected by climate change. As also climate change can affect the river inflow and also increase upwelling events, which can push up the estuary and affect fish. Also, the atmospheric warming can affect the upper levels of estuaries. Therefore, the survival of the white Steenbras and many other estuarine species depend on them being diverse and them being having plasticity so that they can cope with these changes. So the aim of this project is mainly to determine the thermal limits of the juvenile white Steenbras, to classify the individuals into distinct physiological phenotypic groups, and also by identifying these dominant physiological phenotypic groups, we can, within the population, researchers can better understand and better predict what's going to happen to the population in the future. So, wait, does it? Okay, yeah. Video please. Okay, so the fish were collected, 21 white Steenbras were collected from the East Kleinemonde Estuary. They range from 14 centimeters to 26 centimeters. They were captured using a sei net as seen in the video on the side. The East Kleinemonde Estuary is situated 25 kilometers that way towards Port Alfred. Once they were caught, they were put into a 1,000-liter tank with continuous aeration, and they were kept at low stocking densities, so no other factors that may affect them while they're being transported. So for the fish handling, once they got to the DIFS department at Rhodes University, they were placed in two separate 3,500-liter tanks that were collected to a marine recirculatory system. They were housed at 18 degrees Celsius, and temperature was kept constant with the aqua heat pump. They were acclimated for 2 weeks before experiment began. Water quality parameters were taken every day, and they were fed with a maintenance diet of 4% biomass every 2 days. Oh, sorry, I forgot to play the video. We are using a repeat and measure approach. Therefore, the same fish will be used for two experiments. So therefore, they needed to be pit tagged for easy identification, and they were divided into batch A and batch B. Batch A had 8 individuals. Batch B had also 8 individuals, so 16 in total. For the experimental procedure, with thermal tolerance, there are two main methods. the one method that is used to do thermal tolerance experiments is a static method. This is where the temperature organisms are placed in temperatures that are vastly different from the original or acclimation temperature, while for the dynamic temperature or for the dynamic method, temperature is ramped at a constant rate, for several hours or as long as needed. So for this experiment, a heat pump was used to change the temperature. Also, the heat pump only got to 8 degrees, so ice was needed to drop the temperature further. 4 fish were removed from the holding tanks, and 1 fish was placed in each of the 300-liter tanks. So therefore, for the experiment, batch A was conducted for batch A had CTmax conducted on it first, and then batch B, CTmin was conducted on it first. And at each degree change, and the rate of degree change was 1 degree Celsius per hour, and at each degree change, opercular beats were read. Once loss of equilibrium was observed, that was recorded as the fish's endpoints. And then fish were placed back into holding tanks for a 1-week recovery period, and then placed back in, and then gone back to into experiment where now batch A will have CTmin first, or CTmin, and then batch B will have CTmax. So both batches will have CTmin and max on it. Okay, so from that, these were the results. So for CTmin, it ranged from the lowest being 5.1, the highest being 6. For CTmax, the lowest was 32, with the highest of 33 degrees. So comparing this with other species, or other estuarine species, we can see that the dusky cob there on the right, or top right, that their range is less than the white Steenbras, and also their critical endpoints also lower on each. And comparing it to another sparid species, but this is a marine species, not estuarine dependent, is the Francispadam here on the bottom. And the white Steenbras also showed a larger range and also lower and higher endpoints. But comparing the other estuarine-dependent species, the flathead mullet, there on the bottom left, we see that the flathead mullet had a greater range. So therefore, the mullet will be more resilient to climate change than the white Steenbras. But the figures that were observed for the white Steenbras was in Okay, so from those readings, we know that thermal stress occurs several degrees before endpoints are reached, and by taking the opercular beats rate, which is a certified non-invasive method of analyzing metabolic rate, we've seen that the dotted line you can see there at the top and at the bottom, the opercular beats or the opercular beat rates has increased, showing the onset of stress. And we can see that from each of these 4 different individuals, there is variability between the breakpoints, showing that not every fish will exhibit stress at certain temperatures. Then we took all this information, put it in, and then we used a Rankin percentile method where I assigned a 1 for a low performer and a 4 for high performer. And then this could be now divided into different phenotypic groups. I identified 5 different phenotypic groups, with they being cold-water-tolerant, warm-water-tolerant, overall high performer, overall low performer, and generalist. As you can see, I can't have a pointer now, but fish 309 is the overall low performer, as is lower breakpoint is 14, upper breakpoint is 26. Therefore, in estuaries around here, like in the East Kleinemonde and also in the Great Fish River, temperatures in winter has been seen to go at 13 degrees, so therefore it'll be at stress and will need to move further up or further down the estuary to find optimal habitat. While as the one just above it, fish 305, has a CTmin, not CTmin, lower breakpoint of 7.8. Therefore, it will not need to move at a 13 degrees temperature. It can still be in its optimal habitat. Yeah. Okay. Now comparing all of them together, we can see that with the breakpoints, the white Steenbras has a greater range and also has a lower and greater breakpoints at the dusky cob. But now looking at the Frans Madame has a better breakpoints as it has a lower and it has a lower breakpoint, so it can deal with the cold events better. Yeah, but a study that was conducted by Integra on 40 different species that range from the Orange River to East London showed that adult white Steenbras out of those 40 species is still the most sensitive to climate change. But this is looking at the juveniles. So these juveniles are showing more genetic diversity, and I think will be more resilient than the adult version that was studied in that paper. So this could be due to several different scenarios. As you can see there on the left, this shows that so Port Alfred is just there above where Gqeberha is, PE. It shows that per decade, waters are decreasing from up to 0.4 to 0.2 degrees Celsius per decade. And therefore, if fish are in that area and upwelling events happen, then they'll need to move, or low performers might be affected and therefore might die or remove out of the population. And also, if therefore in an estuary, like I say, upwelling events happened, pushing cold water up the estuary, that could be like 10 degrees. And if this is coupled with a very hot summer and low water flow with hot waters above, this can lead to like environmental squeeze. Therefore, individuals will have to be located in a small area. And now, if this is also coupled with high fishing pressure, therefore this can lead to a lot of the phenotypic diversity being removed from the population. Removed from the population, then therefore resulting in what Integra saw in his study with a very high sensitivity to climate change. So for my conclusion, it is essential that we protect these phenotypic diversity by clamping down on our management of the species and of the fishery. Also to prioritize certain estuaries, because certain estuaries have different temperatures, therefore can produce different phenotypic groups or main phenotypic groups, and then bolster the whole marine population or adult population as a whole. Therefore it's essential to incorporate this physiology into the management. So thank you to everybody who was part of this study.
Thanks, Tristan. Questions? How long after you transport the animals, how long did you give them to acclimate?
I gave them 2 weeks to acclimate before experiments began, so they can get accustomed to firstly the temperature, because the estuary they came from was at 15 degrees, so first I had to acclimate them to 18 degrees, and then also the estuary they came from was at, I think it was 18, salinity was 18 parts per thousand, so I had to bring it up to 36, so it was at like marine open estuary standards.
And have you done any work comparing oxygen consumption at the two salinities?
No, haven't. But they'll need to also be done, and a study I think is essential also to do a study on the breed stock or the adults to see how, if they differ, if there's any loss of genetic diversity between the two populations.
Look at the audience again. Yeah.
You mentioned that, thanks for a great talk. You mentioned that juveniles might have a broader thermal range compared to adults. Why do you think that is?
Okay. if I said that, I'm sorry. Like, I think I was trying to say that might have a not broader thermal range, but there'll be juveniles will be more resilient because they still have all the phenotypic groups, as also the juveniles that were sampled in the East Kleinemonde Estuary. There's not a high fishing pressure, so therefore they still have all the phenotypic groups. So therefore, if there's high fishing pressure at a low temperature, then you're going to catch all the cold-water-tolerant and the overall high performers. Therefore, you're removing it and making it more, so less diverse. So therefore, if that estuary opens, or if it's in an open estuary with high fishing pressure, then the diversity might be less. Therefore, the adults will be more at risk to climate change than estuaries that aren't as heavily targeted by fishermen.
Thanks, Tristan.